So now we turn to quantum computation, and what this really means is that we set ourselves a new goal. Instead of transmitting some information from one place to another, we want to take it as an input and process this by something which we typically call an algorithm into a certain output. And the best way to think about this output is that this is the answer to a certain question that we can ask about our input. So this is a certain answer to what is typically a mathematical question. And this is of course one of the key strengths and purposes of a classical computer, but now we want to achieve this by using a quantum system. And indeed employ quantum effects to obtain the answer in fewer steps. And now there are of course so many interesting questions that we could ask, and therefore this will be a rather diverse chapter. We are going to start out by demonstrating that we can achieve at least the same things that a classical computer can achieve. And we will illustrate this for the example of adding binary numbers in a reversible way. At this point we are not making use of any quantum effects. This is simply to illustrate that we can get away with reversible gates, and so we are not yet gaining anything. But this all changes as soon as we make use of superpositions and entanglement. And in order to prepare ourselves for applications where this occurs, we are going to revisit some key features of Hadamard gates and function gates. And what we are going to do there is to simply collect some results that we have already encountered before and bring them into a form that will be useful for the subsequent applications. And our very first application will be the so-called Deutsch algorithm and its extension, which is known as the Deutsch-Jose algorithm. This is a very nice algorithm because it demonstrates a significant speedup for a very simple question and with a very simple circuit. And while the particular question it addresses does not have any immediate practical use, this algorithm already contains the key elements that we will encounter in some really important algorithms. And this in particular applies to the Grover algorithm. This is the so-called quantum search algorithm, and what it achieves is to locate entries in a database in far fewer steps than is possible in the classical setting. And finally, we are going to introduce a very versatile tool, the so-called quantum Fourier transformation. So this implements a certain mathematical operation which is central to many classical algorithms and manages to speed this up significantly. And this has in itself many applications, and indeed we are going to study 4 of them. Phase estimation, quantum counting, period finding, and prime factorization. So here we have 3 very specific and technical terms, and these we will have to clarify when we come to these applications. But they all build up to something which is very common and familiar, namely prime factorization. And this is indeed a very important problem. We already mentioned it very briefly in the context of one-way functions, so certain functions which are very complex to solve for a classical computer. and are employed, for instance, for asymmetric key cryptography. But with a quantum computer, we can speed this process up significantly by an algorithm which is known as the Shor algorithm. So we are going to indeed discuss this algorithm, and this will mark the end of this very diverse chapter. So let us turn to the question whether a quantum computer can achieve at least the same things that a classical computer can achieve, even though quantum computers work linearly and reversibly. And we are going to illustrate this for one specific example, namely adding two binary numbers. First, we are going to identify the detailed steps that we need to carry out this operation, and then we are going to translate them into a reversible setting. So just to start out, let me write down two binary numbers, really selected pretty much randomly, and add these up as we normally do with numbers. So here we have 1 plus 0, which is 1, 0 plus 1, which is also 1, 1 plus 1, that's really 2, so that would be 1, 0, and what this means is that we have carried over one bit to the next step. Then we have 1 plus 0, that's another 2, so another bit carried over, but there is just zeros added to this, and then we have 1 plus 1, which is 2, which we can write down like this. So this is the result of our calculation, and we really went about this in the same way as we do with decimal numbers. And of course, the result should be exactly the same when we start out with decimal numbers in the first place. So let us briefly verify this. Well, our first number here, this is 1 plus 4 plus 8 plus 32. 8 plus 32 is 40, and then we have 5, so this is 45. And down here we have 2 plus 4 plus 32, so this is 38. And down here we have 1 plus 2, that's 3, and 16 plus 64, that's 80, so we have 83. And yes, this indeed works out nicely. Now when we look at the mechanics of this calculation, we see that this is really elementary, and every point we only operate on these two bits here, as well as perhaps one bit that we have carried over from the previous step. So all that we need to do is to add 2 or at the very most 3 bits at every step. So this is all that we need, so let's look at these steps in a little bit more detail. And let's start out with the case where we just need 2 bits. Well, we write down a little table. So we have these possible inputs. And on the other side, we simply write down the result of x plus y using binary numbers. And there we indeed need again 2 bits, because in the last case we obtain 2, which we write like this. Well, in all the other cases, we could get away with just a single bit, but we want to be general, so include all the cases, including this one here. And now we want to identify the mathematical operations that deliver us these 2 bits here individually. Well, the first case is very simple, because this is just the same as x times y, or in terms of logical operations and gates, x and y. Well, the second bit, really just by definition of what we have done here, is the same as x added to y modulo 2. And in terms of logical operations or gates, this is the same as x, or y. So we can use this and directly translate this into a little circuit, which is known as the half adder. So here we have our inputs x and y, and our outputs are simply x times y and x added to y modulo 2. And in terms of elementary gates, this then can be achieved by feeding x and y into an AND gate, to obtain x times y, or into an XOR gate, to obtain x plus y modulo 2. So this is all that we need to add these 2 bits. Well, in the case that we have 1 bit carried over, we have a few more possible input situations, which I list all here. So now we have 8 possible combinations. So a slightly larger table, but our output will still be just 2 bits at most. And indeed in this case here, for instance, we obtain now 3, which we can just write like this. Here we have 2, 2, 1, 2, 1, 1, and 0. So we just have 2 output bits at most. So these are the outputs of x plus y plus c, and these can all be specified by using just 2 bits. And just as before, we now need to identify which mathematical operations we need to carry out to obtain these 2 bits individually. So this bit here and this bit here. Let us first look at the last one. Well, just by the definition of what we have done here, this is again the same as adding up all these numbers modulo 2. The other bit is the one that we carry over, and this can be written in the following way, again by adding some numbers modulo 2. And this is designed so that this is 1 exactly when 2 or 3 of the bits are 1. For instance, when x and y are 1, but c is 0, then we obtain 1 from here and 0 from these 2 cases here. So this adds up to 1. And of course, this expression is completely symmetric, so this will appear whenever exactly 2 of the bits are 1. And when all 3 of them are 1, as indicated here, then this becomes 1 plus 1 plus 1 equals to 3. Modulo 2 is again 1. So this works out in all cases. And with this insight, we can again implement this in terms of elementary gates into something which is known as the full adder. So this has now 3 inputs, x, y, and c. And the outputs are simply what I just specified. So these 2 expressions which are given here. And this we can then implement in terms of elementary gates by just making use of our half adders. So there we are first going to feed x and y into one of these half adders, which means at this stage here we have x times y and x plus y modulo 2. And then we feed this result, the lower entry, into a half adder with c. Well, down here we then already have x plus y plus c all added modulo 2. So this is one of the 2 results that we want to have at this point. At this place here we now have x times c added to y times c. And this we can now feed into an OR gate. Which will indeed deliver us the other result. Let us verify whether this indeed works out. Well, mathematically, the OR gate takes the sum of the 2 inputs, and all the sums can be taken modulo 2, because the output will just be a single bit, and subtracts from this the product of the 2 inputs. So there we subtract x squared y c and x y squared c. Well, this is all modulo 2, as we still just talk about a single output bit. So we can write it also like this. And x squared is the same as x when we insert 0 and 1, and the same applies to y. So these 2 numbers down here are always the same and either add up to 0 or 2, but modulo 2 we can then simply neglect them. So this is then indeed the same as we have here. And this works out too. So this is all that we need to add such numbers on a classical computer. And for a classical computer, this is indeed a very simple task, including that if we add additional bits, this problem does not become much more complex. So if we add one additional bit to these numbers become potentially twice as large, but we just need one additional step. And if we add 10 bits, the numbers become about 1,000 times larger, but we just need 10 additional steps. But the way that we have implemented this here is irreversible. And indeed, addition is an irreversible operation because x plus y is the same as y plus x. So let us see whether we can also implement this using reversible gates. And this can indeed be done by using the controlled NOT gate, so our C NOT gate, as well as our doubly controlled NOT gate, which we also called the Toffoli gate, and some additional bits that we will use to keep track of some additional information in the same way as we introduce them to represent general functions in terms of function gates. These gates here can be interpreted both as classical gates as well as quantum gates. And so we can indeed achieve this both on the classical level as well as on the quantum level. But for concreteness, let us use quantum notation. And we start with the half adder. So for this, we have two input quantum bits in states x and y, and we need one additional quantum bit that we initialize in the state 0. And then we feed these first through a doubly controlled NOT gate, where x and y serve as the control quantum bits. And what this achieves is that this quantum bit down here changes its state exactly when x and y are 1. So the state that we obtain at this place is the state xy. And this is of course already one of our two desired outputs. These two quantum bits are still in the original state, because they were just the control quantum bits, but we now feed them into a normal controlled NOT gate. And then this quantum bit here changes to the state x plus y, which is indeed our second desired output. This quantum bit here remains in its original state, and in this way we retain some information about our original inputs, which makes this implementation of the half adder reversible. In the classical case, the full adder involved the half adder, which we now can implement, as well as the OR gate, which is also irreversible. And now we think that we might need up to 3 additional quantum bits, but again we can achieve this by just one additional quantum bit. So now we have inputs x, y, and c, and one additional quantum bit, which we are again initializing in the state 0. And first we are going to use again a doubly controlled NOT gate, which simply mirrors the controlled NOT gate that we have in the half adder. So this is circumnavigating this carried over quantum bit here. What we have at this stage is the states x and y for the control quantum bits, and c here, and down here we have again x times y. Next we use a controlled NOT gate between the first two quantum bits. So again this is just as in the half adder. So what we have here is then still x and x plus y, while nothing has changed for the two remaining quantum bits. Now we use a doubly controlled NOT operation with two controls, namely these two here. So this has an effect on our last quantum bit, which changes its state from x plus y when the other two bits are 1. So we have to add their product to this. And this we can now multiply out in this way, which is therefore identical to one of our desired results, namely this one. These two quantum bits have remained in their state. And we now combine them again by a normal controlled NOT operation. So this changes this state here into x plus y plus c. And this is indeed the other desired output. And finally, we have 2 additional quantum bits. And these simply retain some information of our inputs. In particular, from these we can reconstruct x and y. So this is a fully reversible implementation of our full adder. Now we should note that at no point within the circuit we use superpositions or entanglement. We always remained in computational basis states and therefore states of definite information. And this means that we can interpret this whole process also in terms of classical states and classical gates. And indeed we have not gained anything, we only have shown that we can also achieve this by using reversible gates. But all of this changes as soon as we are going to use these quantum effects, and this is indeed what we are going to turn to now.